Okay, so what we are going to do is continue on our conversation for last time. What did we talk about last time? Yep, exactly. So we find the margin of error and we construct this confidence interval. So it's important. What we're going to be doing today is we're going to be building our terminology for as we talk about something called hypothesis testing. But in order to get there, let's start a little bit about this confidence interval and we'll see how this relates. So, that's a pretty good one. Pretty good. Not great. Let's imagine that I run a company and I have this online retail store. Maybe I do this through Amazon or whatever. And I have this information on my description about what this is for what I'm selling, and I have this nice detailed description and some ratings and so forth. And I've noticed that I average about 10% returns. 10% of my sales come back to me in the form of return. That's really annoying, by the way, right? With Amazon, if that happens to you and you're selling through Amazon, Amazon will charge you fees and everything whenever a customer returns stuff. So you would like to reduce those returns. Now, I know, too, from the data I've gathered, because I gather a lot of data, I know that it's not always 10% month to month. Right? Maybe this is a 10% per month. Maybe I have plus or minus 4 percentage points. So what would my at say 95% confidence interval? I have plus or minus 4 percentage points. What would that mean? What would be my range? What would my range be? Not complicated. Yeah. Exactly. That obviously equal distance. So what does that mean, 6 to 14%? Yeah, but you're right in the sense that it does capture, there's a 95% chance that any given month my return rate is going to fall within this range. There's a 95% chance. Well, like if I cover 100 months, five of those months will be outside of the range, and then 95 of these months will be inside this range. Right? That's what that means. And there's a 95% chance that what's going on will be somewhere in there. Now, let's imagine that I go through this is really high. This 10% average, this is really high. I'm going to go and I'm going to change all my descriptions to give a lot more detail on all the things I sell. To tell things like exactly what it includes and what it doesn't include, to give things like product dimensions, to just make it really abundantly clear. And then after the first month, I find that my return rate is, let's say, 5%. What should I conclude from this? So this is historically what it's been. And then I change something about how I present my product. And at the first month after that change, I now have 5% return rate. I like that. So something I did actually affected the return rate.
Because it's out.
Exactly, right? So in other words, one possible thing that can happen is that my changing of the website has established a new normal. And now it no longer focuses on 10%, and that based on this 5%, right, this 1 month of averages, based on that 5%, this is the new normal. And we have a new distribution. But it is also possible that nothing changed. It's, yeah, there's a 95% chance it'll be over here, which means there's a 5% chance it'll be over here on the tails. And so maybe that 5% here is just due to randomness. And that is so much of what statistics is. You are trying to discern between, hey, you have this weird sample. Is this sample average just unusual because of random reasons, in which case you're just pulling from the new distribution, and what is different about this sample doesn't really matter. Or maybe that difference does matter, and you are actually pulling from a new distribution. The question is, in this case, that 5% is what we call statistically significant. It is probably not due to randomness. But if I had maybe 7% return rate, because it falls within my 95% interval, if I had a 7% return rate, then we would say it is not statistically significant. It is probably due to randomness. That's when we talk about confidence intervals and thresholds, that's what hypothesis testing is. As we'll talk about next week, hypothesis testing involves running a bunch of numbers to get some calculated value, and then comparing it to the critical values we've been talking about. And if the absolute value is less than those critical values, it's not statistically significant because you haven't gone far enough away from the mean. If they're greater than those values, then you've gone far enough away, and you probably entered some sort of weird world where it's possible it's random. It's possible it's just due to randomness, right? 5% chance it's due to randomness here. But, possibly not. Probably not. Probably there's something really interesting going on. And so what we're going to be doing today is going over a lot of the terminology statisticians use to describe this. And so then we can get familiar with it as we then do the next stage, which will be next week, and we actually do the numbers. Any questions so far? Great. Yeah.
So you said that if the absolute value is lower than mean, it's not the answer?
It's lower than the critical values.
Okay.
Yeah. Let's go over what those critical values are. So we have a confidence level. With a corresponding alpha. We have Z alpha divided by 2 for 2 tails. And today we are going to introduce a new terminology, the Z-score for 1 tail. A 2-tailed Z-score is just what it sounds. Like what we've been talking about. The area that you care about, the alpha, is divided into 2 sides. If the alpha is 0.05, for example, then, or 5%, then 2.5% over here and 2.5% over here. If it's 1 tail, draw this well, and the alpha is only on 1 side. It can be on the left, it can be on the right. So let's go over our 95%, 99%, 99.9%. I have to get rid of this part right here. What is the alpha at 95%? 0.05. Thank you very much. 0.01. Excellent. And you got that how, Amanda?
How did she get that result?
How did she get that result? Do you remember? 5%, 0.05, 0.01, 0.001. What? How?
That's what he's asking.
Okay, well, I'm asking you because we talked about it. How? Yeah?
You just subtract 100%.
You just subtract. So remember, alpha is everything that is not this confidence level. Because this is 95%, then 5% is what's left over in the tails.
and we express that alpha as a decimal, right, rather than a percent. Because we're gonna, you put into Excel, you work with decimals. Honestly, the fact that we call these percents is kind of just a weird colloquialism. This is where the conversation is. We typically talk in terms of things less than 1 when we're talking about percents. Just like we were doing confidence intervals for proportion. You don't put, 30 in the equation. You put 0.3. So that means this is 1. This is 0.1. Any questions? 1%, 0.1%. Great. So do you remember what the z-score was for alpha divided by 2? 1.96. And 2.576. And exactly 3.291. Now, over here, on a standard normal distribution, to get, let's say, 95% confidence in the middle, we go 1.96 standard deviations this way, 1.96 standard deviations this way. We talked a lot about that when we were doing the empirical rule and stuff like that. If you want 99.9%, then you go 3.291 and the left, 3.291 to the right, leaving that 0.001 on these two sides. With a one-tail z-score, do you think it's going to be larger or smaller than the two-tail z-score? Small, why? Yeah. Right. Like a one-tail, by definition, does not take alpha divided by 2, which means a larger alpha value is here. Right. Here, for 95% confidence, this is 2.5% or 0.025. Here, it has to be 0.05 because the entire alpha is shoved on one side. Because the entire alpha is shoved on one side, we make it a little larger. Right, it has to be. So this area right here is going to be larger than this one, which means we are going to be scooting to the right, and therefore this distance gets smaller, which is why this is 1.645. .326 for 99%, and you don't have to memorize these either in case you're curious, because obviously I can't. 3 points. So we are not. They are things that will be provided for you on your exam. They're things that are built into Excel too. You can find them pretty easily. Just don't take the alpha divided by 2. Any questions? Okay, let's talk about when you'll use one versus the other. I think I'll lose this. I have to keep that piece. So in a lot of, I did this first. In a lot of hypothesis testing, there are two basic questions you can be asking. One is you can be asking, is this thing unusual? What happened? Is this thing different in some way? The other question is this thing better in some way? And those are two very different things. Unusualness can go in two different directions. Something can be unusual by being a value being overly small or being overly large. Improvements, though, only happen in one direction. If you want faster pizza delivery, faster means better. That means a lower value, a lower time. More sales, a higher value. So we call these two-tail tests. One is for unusualness. One-tail test, which is for improvement.
An example of a two-tailed test. How much ketchup is usually in a bottle of ketchup? I was going to look this up, but I forgot to. I don't remember. Anyone? 40 ounces, thank you. So, maybe shopping at Costco. Or is it 40?
About 40 ounces.
Okay. 40 is what 40 can work. I don't really care as long as it's not crazy different. 40 is fine. Like I've seen I only mentioned Costco because I've seen the bottles at Costco and they're huge. And given your reaction that 40 seemed rather large, I'm like, that's probably the Costco's one. I don't know. Let's just say 40. So a machine puts it's not done by hand. A machine puts 40 fluid ounces, 40 ounces, probably fluid ounces, right? Ketchup is kind of a viscous kind of thing. So 40 ounces in the ketchup bottle. It does that all day. Now, the machine can make two different kinds of mistakes. What are the kinds of mistakes the machine can make? Put too much and put too little. So in that case, it is a two-tailed test. If we're wondering if the machine is problematic in some way, if it needs to be fixed, if it needs to be cleaned, we can grab, like, say, 10 bottles of ketchup and measure with a super precise machine exactly how much ketchup is in each bottle, and then get an average, a sample average. And then if that sample average is way too low, or the sample average is way too high, we come to the same conclusion regardless of something wrong with the machine. That would be a two-tailed test. We're checking to see if the amount that is put in the bottles is unusual. A one-tailed test would be something more like, let's see if we can change the machine so that it does its job faster. If it does its job faster, then lower values, time, how long it takes to squirt things in, that is an improvement. If we change the machine and it takes the same amount of time, or we change the machine and it takes more time, then we know that our change was not a good change. So note that when it's the same or greater, then that is boring. That is not unusual. That is not something we're looking for. It's only when it's less. That's when things are an improvement. That's when we say, oh, let's change all the machines now because I figured something out. Any questions on that? Now this process is called hypothesis testing, which means we need some hypotheses to work with. We have something called the null hypothesis. And the alternative hypothesis. Also known as H dot and HA, or looks like hose and Haas. How many of you have ever been to the movies? I would assume all of you. Now, when you are choosing which movie to see, and you just happen to see the title of the first movie, what is your default assumption about that movie? You don't know anything about them. What is your default assumption? To see it or not to see it? I know, but like, what I'm saying is you look at the title, you don't know what the movie is about. So what's your default assumption?
Try to guess what genre of movie you're getting.
Why are you doing that?
To gauge your interest if you want to see it or not.
Uh-huh. In other words, your default assumption is, I don't think I want to see this. And in your case, you're looking to see, get more information about it to figure out if you want to see it. Right? It takes effort or information to switch over to the yes category. I will see that. Right? Your default assumption for movies is not, I just see any movie that comes up. Your default assumption is not whatever title I see alphabetically listed first, I'm going to go see that movie. I'm just going to see all movies all the time, right? Your default assumption is no. Right? And this is what we call the null hypothesis. Right? It's the assertion that corresponds to something that's not unusual, that something is boring. The default position. Like the default position for anyone going to the criminal justice system is that you are innocent until proven guilty. The null hypothesis is you're innocent. Right. And then the burden of proof is on the prosecutor to say, no, this person voted it. It is the boring position when nothing's happening. So like, for example, if I was curious how I can improve how well people do in the course, I might decide to create another practice exam. Currently, there are 2 practice exams for every exam. So like, maybe if I make a 3rd one, I can result in people doing better. My null hypothesis is that that will not make a difference. It sounds like bitter and cynical. I'm not saying that's like literally what I would be thinking, because like why am I making another practice exam if I don't think it'll help? But the statistical default position is it doesn't matter. And I have to find the evidence that it does. The alternative hypothesis is whatever the null is not. Assertion for the unusual or improved position. My alternative hypothesis will be like, adding an additional practice exam will make the students perform better. Resist the temptation to think that a null hypothesis just corresponds to whatever your intuition is. Like the intuition is if you exercise more, you will lose weight. But the null hypothesis is not if you exercise more, you will lose weight. What would be the null hypothesis in that situation? Yeah? Exactly. Or not only will you not lose weight, nothing happens, right? So you won't gain weight either, right? I mean, it depends on if you're one entry tail test, but you're absolutely right. But the null hypothesis is nothing matters, essentially. It's a very nihilistic view of the world. Now, what the null hypothesis is does change a little bit, whether we're talking about a two-tail test or a one-tail test. So as a way to get some of our terminology down, let's come up with some. Let's say, for our ketchup bottles, the null hypothesis is that the ketchup bottle works fine. Or the machine works fine. The null hypothesis is mu equals 40. What would be the alternative hypothesis? Not equals. Mu is not 40. We can also do the same thing with the proportion we did. What was our, so if mu was for general averages, what is the symbol for the population proportion? Pi. You said pi. Pi, okay. Audrey is right. Remember, it's pi. Pi is not 3.14, 159, 26535, 787. Of course, pi is a variable. It might be, say, 30%. Like a candidate is trying to, that's not a great example because they'll be looking for improvement. We'll say like maybe 30% of our customers like some particular cupcake that we sell, 30% buy them, and so we change the cupcake. We naturally want to know if they like it more, but we also want to know if they like it less. If they like it less, we should probably return to what it was before. If we like it more, then we probably should not return to it. But if we change it, then maybe it doesn't matter. So the null hypothesis is that, and the alternative would be not 30%. Try to come up with the unusualness ones because in business, we're often thinking of improvements. We're thinking of ways to make things better. A cupcake one felt like kind of an improvement. I'm trying to think of what would be a better one, but it's not coming to me right now. Any questions? All right, then let's do one tail. One tail, this is much easier. Let's imagine that I'm selling a certain amount of maybe on average, my customers are buying $50 on average from me. So every customer buys $50 from whatever I'm selling. The average receipt is 50. Maybe it's a nice restaurant or something. What would be, if I'm trying to improve my sales, what would be my null hypothesis? My sales won't change. Or I'm trying to improve my sales, so
It's less than or equal to.
Less than or equal to. Like, apparently restaurants know how much money each table brings in. So they know the average check per table. And sometimes there's apparently consultants which restaurants will hire, which are like table experts. And they know things about like the psychology and how people feel about the tables and like if they're near a window and everything. And like maybe if you put the tables too close together, that has one effect on revenue. If you put them too far apart, that's another effect on revenue. If you make the table too high or whatever, the seating. And so I know, right? It's the division of labor is limited by the extent of the market. It's crazy. I had no idea this job exists, but they exist. And so maybe someone is like trying to change a table. This is a real story that I heard about. I think it was Planet Money did a story on this. And there was a restaurateur who had one table that they thought would be really great, and it wasn't bringing in a lot of money. And so they hired this expert to see if they can figure out how to fix it. And the expert is like, well, the table's a little higher, and so the customers don't feel like they're really part of the restaurant. So if you bring it in like with the other restaurants, and then they played around with spacing because obviously if you make them too far apart, then you're wasting space, and space is at a premium at a restaurant. But if you put them too close together, then people won't necessarily feel good about eating there. So there's all this like empirical work that this person has done to figure out the optimal spacing. Anyway, so then on this one table, they're trying to improve it. And this is a test for improvement, right? It might get better, it might get worse. We want to know if it gets worse or if it's the same, then that's our null hypothesis. What is our alternative hypothesis? It's alternative. Anyone?
Not less than equal to.
Well, we have another way to put that, right? Rather than not less than, we just say greater than. Remember, the alternative is whatever the null is not. So one way to check, by the way, if you're working with all two tail or one tail, is you're looking at these values, right? Equal or not equal, that's a two-tail test. With a greater than or less than signs, that's a one-tail test. And so what's interesting about this article is they noted not only when they made these changes to the table, the average amount of money people spent went up, but the researcher also said those two critical keywords. Not only was this an improvement, but it was an improvement that was statistically significant. In other words, probably not due to randomness. We can do another one too for my returns. So what would be my null hypothesis in trying to improve my return rates? I'm talking about if I'm trying to figure out, like, oh, I want to improve my return rate. It was 10%. I want to make it better. What would be my null hypothesis? So is a higher return rate an improvement? Is it a higher return rate? Is a higher return rate an improvement? No. Why do you say no? Yeah, because remember, like, as someone who is selling something, if people return it to me, then not only do I have to give them their money back, but I also have to, like, it kind of represents a failure. I could not have sold that to someone in the meantime who would have kept it. I have to pay Amazon to restock it, or maybe I have to, or maybe if it was my own store, I'd have to pay to restock it. Companies do not like it when customers return things. They only do it because if you couldn't return things, you never buy stuff in the first place, so they have to. I'll make that option, but generally speaking, I want fewer returns. So my default assumption is, or my any change I make will either increase or not change my return rate of 10%. It's a weird looking house. What's the alternative hypothesis? Yeah? Not equal or less than, because remember it has to be whatever the, but you're right, it will be less than. Okay. Emily, let's imagine you are working for a company and you work in HR, and you help hire people. Now, there are two kinds of mistakes you can make at your job. What are those two mistakes? You can just name one of them if you want. Think big in the terms of you're hiring someone. What are one of the mistakes you can make? Yes, you do. Think about it. Like, let's imagine you hire somebody, and what would be the worst case scenario for you? But just from your perspective. Like, you hire someone, you're like, this person is really great. There'll be a really great person who works in IT. And then that person who works in IT, like, shows up, like, drunk and high every day. Would you consider that a mistake on your part? Yeah. Right? And people are like, who hired this idiot? Right? And Emily's like, someone else. So mistake number one that you can make is you hire somebody who you never should have hired. What's another mistake that someone can make?
You didn't hire someone that you should have hired.
Exactly. You didn't hire someone you should have hired. These are what we call type 1 and type 2 error. And they have lots of applications beyond that. If you decide to convict somebody who's actually innocent, that's type 1 error. If you let a guilty person go free, that's type 2 error. If you decide to watch a movie that turned out to be terrible, type 1 error. If you decide to not watch a movie, that is awesome. That is type 2 error. You missed out on something cool. type 1 error is we reject the null when we should have failed to reject it. Your null hypothesis, Amanda, for any random, for Emily, I'm sorry, for Emily, for any random person who comes in the door, is you're not going to hire them. But for that person who ended up being drunk and high all the time, you rejected your null of not hiring when you should have failed to reject. You should have stuck with your null. You said, you're going to be a great fit here. And then they're like, yeah, sure. And then they set something on fire, right? Like that was a mistake. We assume people are innocent until proven guilty in our justice system. If you reject your null and convict an innocent person, you have made a mistake. Exactly the same kind of mistake. You did the unusual thing and you shouldn't have. You go to see a movie, that really sucked. Exact same problem. Bring it down here, a lot of wall space. Type 2 error. You can probably guess what type 2 error is. Anyone? Yeah. Exactly. You fail to reject the null. You should have rejected it. You failed to reject the null when you should have rejected it. So you should have rejected the null and put that guilty person in jail, but you failed to reject it and they now go free. You should have not passed on that really amazing employee who is really friendly and great. You should have rejected your null hypothesis there and hired them, but you failed to reject it and you decided to not hire them. You should have gone to see this movie, which is really amazing, but you failed to reject your null hypothesis and did not go see it. You stuck with the null hypothesis, the default boring thing, and you should have done the unusual thing. You should have rejected it. That's type 2 error. Any questions? Yeah. Of type 1?
Okay, this is my favorite one.
The FDA is in charge. The FDA is in charge of approving or rejecting drugs, right? So one error that they can make is that they will approve a drug that is actually pretty dangerous. That maybe it has a lot of risks associated with it or something like that. That is a type 1 error because their null hypothesis is not approved drugs. The null hypothesis is saying no. Right? That's the default position. And they rejected that and said, okay, you're going to go for it. And we were going to approve the drug and release it out to the public. And then that was a mistake. What would be type 2 error in this case? The FDA approval. Exactly, doesn't approve a drug that's beneficial. They stuck with the null hypothesis, saying nope, we're going to fail to reject the null, and you're going to have to shelf that, potentially great cure because we think it's too dangerous, and it turns out it's fine. Does that clear things up? Yeah. I can do this all day. There's a million examples. It's whenever someone makes a decision, right? There's two different kinds of mistakes you can make. You can do the unusual thing, and then that was a mistake, or you can not do an unusual thing and miss out.
You go on vacation with your friends, and it's a disaster, type 1 error. You miss out on an amazing
Vacation with your friends, type 2 error. Now, which of these do you think is the bigger problem in sort of practical reality? Which do you think is the bigger problem? Type 1, why?
That's like for an example.
failed to go on a vacation, you just missed out on this vacation. Well, if you go on vacation now, it's terrible to the next thing.
That's true, but think about what happens if you go on vacation that's terrible. You can leave, right? And in the case of the drug approval, if it turns out the drug is harmful, what happens with the FDA? They do a recall. They can remove it. But if it turns out that they did not approve something that was amazing, what happens? Yeah, we don't know. Right? We don't even know they made a mistake. So one of the things, by definition, because you're doing the unusual thing, it's very clear that a mistake was made. And because it's very clear a mistake is made, it's a little easier to fix. I see what you're saying with like the vacation example, and you know, it can be, sometimes it can be easy to fix that mistake. Sometimes it can be hard, depending on where you're going. But generally speaking, because type 2 errors are easier to spot, they are less of a deal. Oh, you hired someone you shouldn't have. We'll just fire them. And then we're done. Well, if you don't hire the amazing person, you never find out about it. There are some exceptions to that rule. Like all of those like publishers that rejected Harry Potter, saying we're not going to do Harry Potter, that's stupid, right? And they passed. They made type 2 error, but because Harry Potter ended up being super famous later, that's the only reason why they found out they made type 2 error. If it was a moderate success, they never would have learned. Who's that idiot that said no? This is why, like, there's concern. Like, FDA sometimes has criticisms that they are too loosey-goosey with approvals, that they will approve drugs with little evidence, and that certainly happens. But there's this other pressure that they are sometimes too stringent, that they will say, no, we're not going to approve this drug, because they know there will be no public outcry. Right? Here, the mistake is obvious, and so there's public outcry, and they're embarrassed. Here, because the mistake is sneakier, people might not notice that they made a mistake in the first place. Yeah, Michelle. I would say this one is more dangerous, because this one, because the mistake is clear, then you can fix it. And you can fire the person, right? Or in dating, right? You date someone, turns out you don't like the person, you can just break up with them. Right? But if you never date the person, that's amazing. You never find out you made a mistake, right? There's that song. I was just listening the other day, the Avril Lavigne song about the skater boy. You remember the skater? I don't know. Maybe I'm just too old. Maybe. What?
I was going to say,
I just happen to be listening to this skater voice. I don't know even know what I was listening to. These really help listen to that music. But
music choices he thinks Excuse me.
I love the Admiral myself. I'm just wondering how you just come across Admiral. Unless you're looking up old 2000s playlists or something.
I don't know. For some reason it popped in my head and I wanted to listen to it. I think so.
Wow.
And so, well, there's a lot of great economics too in some of her songs. This is song.
This is like the biggest excuse.
No, there's this song about the oh crap with the I think it's called Girlfriend.
Yeah, it is.
Yeah, that's a song about opportunity cost. Right? That's like, you know, your opportunity, yeah, you're dating this girl, but I'm better, and your opportunity cost is high.
Economics is everywhere. And so is stats, right? Because, you know, she's talking about type 2 error with this guy. You know, with the skater boy guy. It's type 2 error.
All right, any questions? Besides, what the hell are you listening to now? Let's see. What was something else I wanted to mention? Really quick. Oh, yeah.
Another way to think about what type 1 error is it's also known as alpha. It's also known as alpha. Go back to my original example. 10%, 6%, 14%. If I have a % rate of return, it is possible that's the new normal. It is possible that that is the new standard. That what I changed really made a difference. And in this example, at 95% confidence, if I can move 95% right here, I would claim that that is a statistically significant drop. However, it is also possible that it's not a statistically significant drop. Right? It is also possible that it wasn't a genuine improvement, I should say. It is also possible it was not a genuine improvement. Why do I say that? Well, but in that case, then are you saying that that was just a coincidence? Okay. So yeah, so in other words, what you're saying, Amanda, is that 5% is just random, right? That it just randomly got low, right? 95% of the time, it is in this range, which means 5% of the time, due to random events, it is not in that range. In other words, there's a 5% chance I'm using 5% twice, but there's a 5% chance that this low rate of return was just a coincidence. In other words, if I were to say, oh, look, it's outside of my 95% confidence, it's outside my 95%, so therefore it must be an improvement. I'm like, well, but there's a 5% chance that it was just weird, right? And that's that alpha. I would, under these circumstances, reject my null hypothesis and say my changes to the website made things better. But I have to recognize that it is possible that it was just coincidence. So there is this, does anyone know XKCD? The webcomic, yeah. So it's I guess famous among some people, webcomic that talks about like math and statistics and science and a bunch of stuff, but it's funny, you have to trust me. And there was one comic that said, I think this one's actually on my door, that had some scientists talking, and they're like, we think that jelly beans might cause people to live longer if you eat jelly beans. And they were like, oh, well, that's interesting. And so then they checked, and they're like, no, it doesn't seem to matter. And someone said, no, I think it's one particular color of jelly beans. It's one particular color that does it. And they're like, oh, okay. So let's try red jelly beans and blue jelly beans and green jelly beans and black ones and purple ones and striped ones. And they test 20 different jelly beans. And then out of one of them, they say, oh, this did make a difference. This is what matters. The green ones matter. What's the problem with this? What is 1 divided by 20? 0.05. Right? In other words, if you test a whole bunch of things, by random chance, 5% chance, you're going to get something that is statistically significant. Right? And so them claiming that green jelly beans are really amazing is not an example of good science. It's just an example of type 1 error. It's just an example of alpha. A weird thing happened. So this is sometimes a way to lie with stats, is you just run a bunch of experiments until the random thing happens. And then you claim that you've discovered something neat, when of course it was just random, right? Don't be fooled by randomness. Right? Don't be fooled by randomness. It's a huge, big lesson in stats. Next class, then we are going to be doing some calculations to actually determine what's statistically significant or not. Here's the basic process of how that's going to go, so I can just prepare you. You will have a calculated value. That's going to be a z-value you find based on sample average, sigma, etc. Right? And etc. It's essentially a standard deviation for the standard normal distribution adjusted by n. So in other words, we're going to do a bunch of math. We're going to take the difference between what we would expect and then what we empirically saw in the sample, and then we'll throw in a standard deviation, and we'll throw in the square root of n. And we're essentially get a z-score. And this z-score, this calculated z-score, will be then take the absolute value. So you will compare the absolute value of the calculated score, the calculated value. I use score and value, I'll just say score so I don't get confused with the value here. With the calculated score with critical values. And these critical values are right here. If the calculated value is greater than the critical value, it is statistically significant. In other words, we reject the null hypothesis. If the calculated value is less than the critical value, it is not statistically significant. We fail to reject the null hypothesis. I'm just going to show you this with a two-tail so you can maybe visually see where I'm getting at. Some of these black markers are good, and some of them are not. What? I sometimes do, no, I usually do, and then I think they got mixed up with the ones that were here, and I can't figure out which one's mine. That's okay, I'll just use this green. Let's imagine, for example, that the margin of error for 95% confidence was, I don't know, 5. That's really big. Let's imagine it's 0.5 because, come on. We have 39.5 in one direction, and we have 40.5 the other direction. The idea is that you are essentially taking this information and normalizing it into a standard normal distribution with a mean of 0, standard deviation of 1. And so if your sample average is, say, 40.2 or it's 39.9, you're in this range. You don't go far enough. Your values will be like, 1, or your z-score might be like 0.86, and it's not far enough to get over past these thresholds. But if your average is, say, 40.8 or 39.1, now you have passed these points, which means your corresponding z-scores will be the absolute, take the absolute value of them, and the corresponding z-scores will be greater than 1.96. It's far enough away. That's why we take the absolute value. We are concerned about distance. And we're essentially using this model, this standard normal, as something to be able to standardize our approach to figure out what's weird and what's not. Have a great weekend, everybody. I will see you then next time, and we will actually dive into the math here.